Assalamu alaikum. I am Jahangir Alam, lecturer in physics. I welcome you all in my online class. First of all, thanks to Almighty that I am still all right and carrying on my regular activities. Dear students, I also hope all of you are all right and carrying on your regular studies, staying at home. Dear student, expressing my good wishes for all of you, I am going to start my today's class. And in our today's class, we are going to discuss some important and realistic topic from the 4th chapter of physics, first paper, right? So we are going to discuss from the chapter of Newtonian mechanics. And in our today's class, mainly we will discuss on circular motion or angular motion, some expression related to angular motion, some mathematical problem and creative questions. And I hope you will be benefited from our today's class. So dear student, let's start our class. Right. Dear student, in our today's class we are going to discuss mainly about rotational motion or circular motion and terms related to circular motion, that's our angular displacement, angular velocity and angular acceleration. Dear student, you know from our previous discussions or videos, we have learned that we have discussed about the motion or linear motion, that is when a body moves along a line. When a body moves along a line, suppose a body is moves from A point to B point, if the length of the distance or travel path is considered, then this type of motion is called linear motion or simply motion, right? But when a particle or body moves along a circular path, suppose a body moves along a circular path, or when a body moves centering a point, when a body moves centering a point, then this type of motion is called rotational motion or angular motion. So dear student, and when the body moves along a line, suppose point A to B, then the length of the path is denoted by S. This is distance of a moving body. Distance of a moving body or simply linear distance of a moving body is denoted by S. But when a body moves along a circular path, suppose the body starts from A and after a certain period the point or body moves along at point B. So the length of the arc AB is the linear displacement, which should be expressed by S. But the angle subtended by the arc of the circle or circular portion at the center theta, this theta is called angular displacement. So angular displacement should be denoted by theta, that is angle created by the travel path of a circular path is known as angular displacement. So dear student, angular displacement is denoted by theta. Here the unit of the linear displacement S is meter, but the unit of the angular displacement should be expressed in degree or radian. So for more convenient in maximum math or discussion, we will use the unit of theta as radian, right? So unit of angular displacement is radian, right? Now we are going to discuss about the angular velocity. So dear student, in linear motion, you know distance traveled by a moving body in unit time is called displacement or velocity or linear velocity. Or in other word, you can say that rate of change of displacement is called velocity or linear velocity. So similarly, in case of angular motion, we can say that angle created by a body moving in a circular path in unit time is called angular velocity. When the linear velocity or simply velocity v is denoted by s by t and its unit is meter per second. At the same time, the angular velocity will be denoted by omega. So, omega will be theta divided by t, because here theta is analogous quantity of displacement s. Here displacement is divided by t, here theta is divided by t. So, unit of angular velocity will be radian per second. Okay? That is when you know angular velocity, linear velocity can be expressed as s by t. Here angular velocity can be expressed by theta by t. But if the body travel or complete one rotation, then the value of theta will be twice pi. So, in that case, the time required to complete one oscillation is called time period. Okay. So, if the angle or value of theta is twice pi, in that case the value of t will be time period. Okay. So, in that case omega is equal to twice pi divided by t. Okay. Again, you know time period t and frequency f, there is a relation between t and f. You know f is equal to 1 by t. So, you can express the value as 2 pi f, because f is equal to 1 by t, right. Again, if the body complete n rotation, in time t, then you know for one complete rotation the angle created is twice pi. So, for n rotation the total angle will be n into twice pi. So, in that case the value of theta will be n into twice pi multiplied by n divided by, here time will be t. So, this is also an expression for the angular velocity, right. So, Gyration, now we are going to see the expression and definition of angular acceleration, right. Gyration, already we have discussed about angular displacement and angular velocity. Now we are going to discuss about angular acceleration. So, before discussing angular acceleration, here I would like to introduce you or remind you the simple acceleration or linear acceleration. You know, the rate of change of displacement or linear displacement is called acceleration or linear acceleration. So, linear acceleration a can be expressed as v minus u divided by t, that is the change of velocity. Here u is initial velocity, v is final velocity. So, v minus u means the change of velocity divided by the required time. So, this means rate of change of velocity is called acceleration, and its unit will be meter per second square. Similarly, the definition of angular acceleration can be expressed as rate of change of angular velocity. Rate of change of angular velocity is called angular acceleration. So, dear student, maintaining the same structure of the expression, angular acceleration is denoted by alpha. Angular acceleration is denoted by alpha. So, alpha can be expressed as omega minus omega naught divided by t. Here omega is final angular velocity, omega naught is initial angular velocity, and t is the required time to change the velocity, right. So, this is the expression for the angular acceleration. These are the basic item of this topic, and unit will be radian per second square, right. Here the unit for the angular acceleration meter per second square, and in angular acceleration, in linear acceleration unit will be meter per second square, and in angular acceleration unit will be radian per second square, right. So, these are the very basic terms related to rotational motion. Now, we are going to see some expression which are similar to linear motion, right. So, now we are going to compare some expression with the linear motion and rotational motion. Okay. Now we are going to see the analogous quantity or quantity which are similar to linear motion and rotational motion. You know, already we have discussed when displacement is expressed for linear motion, it will be denoted by S, and for the rotational motion and circular motion, it will be expressed by theta, right? At the same time, you know, unit will be meter and the unit will be radian. And the velocity for the linear expression is denoted by V. Unit will be meter per second, and in that case rotational motion it will be omega. So it will be radian per second, right? Acceleration, it will denoted by A. Unit will be meter per second square, and in that case it will be alpha. It will be radian per second square, right? So there is now we will see some expression involving S, V, A and T. In the for the rotational motion, it will be the expression related to theta, omega and alpha, right? So first expression, you know, from the displacement, S is equal to V multiplied by T. It will be omega. Theta is equal to omega multiplied by T. Again, S is equal to U plus V divided by 2 into T. It will be theta is equal to omega plus omega naught divided by 2 into T. Again, S is equal to ut plus half a T square. So in that case of rotational motion, theta will be here u naught, that is initial velocity multiplied by time. It will be omega naught T plus half alpha T square, half a T square, it will be half alpha T square. Again, you know, V is equal to u plus a T. Here omega is equal to omega naught plus alpha T, right? Again, you know, V square is equal to u square plus 2 as. Here omega square is equal to omega naught square plus 2 alpha theta, because theta is analogous quantity of S. So dear student, these are the expression which will be used for the rotational motion. These are similar expression for the expression used in linear motion, right? Now we will see some more analogous quantity which are involved in the rotational motion. Dear student, here are some analogous quantity in rotational motion with the linear motion. In linear motion, we use mass, that is the role played by mass that will be in rotational motion will be moment of inertia. So moment of inertia is denoted by capital I. Its unit will be kg meter square. So in case of mass, so that role played by mass in linear motion will be played by moment of inertia in rotational motion or angular motion. So moment of inertia is denoted by capital I, and its unit will be kg meter square. After some time we will discuss what moment of inertia is. Force, that is the effect of force that we have observed in linear motion, that will be played by that quantity named torque. That is the effort which create motion or tries to change the state of motion in linear motion, that will be shown by quantity torque, right? So torque will create angular motion, force will create linear motion, and torque will create angular motion. Okay. Then finally the momentum. In linear momentum, which is denoted by P, unit is kg meter per second, and in angular motion it will be angular momentum, which is denoted by capital L, and its unit will be kg meter square per second. So these are the analogous quantity with mass, force and momentum. Now we can see to expression, there is, you know, in case of force, you know, F is equal to F is equal to ma, that is the product of mass and acceleration. So in case of torque, you know torque is denoted by tau. So tau is equal to here the product of mass and acceleration. So in case of rotational motion, the analogous quantity of mass will be I. You know the mass and I, that is moment of inertia, these are the analogous quantity. So since it is for the rotational motion, so m will be replaced by its analogous quantity I. So tau is equal to I then multiplied by alpha. Here A is linear motion, and in case of rotational motion the angular motion will be alpha. So tau will be I alpha. Similarly, you know momentum P is equal to the product of mass and velocity. So in case of angular momentum L is equal to the analogous quantity of m will be I, and analogous quantity of linear velocity will be angular velocity omega. So these are the expression that will be used in rotational motion. Okay. So now dear student, we are going to discuss two important topic for rotational motion, and that are moment of inertia and radius of gyration. So moment of inertia can be defined as sum of the product of the masses of all particles of a rigid body rotating or rigid rotating body and square of their respective distances from the axis of rotation is called moment of inertia of the body. Dear student, suppose this is a rigid rotating body which is rotated around the axis of xy. Here are innumerable particles. We consider three of them. First one is the mass of the first particle is denoted by m1, then the mass of the second particle is denoted by m2, and similarly the mass of the third particle is denoted by m3, and the respective distance from the axis of rotation are denoted by r1, r2 and r3, right? So from the definition of the moment of inertia, so moment of inertia can be expressed as I is equal to, that is the sum of the product of masses of the particle and square of their respective distance. So sum of the product of mass and respective. So if we consider the first particle, so it will be m1 and its respective distance is r1. So product of mass and square of its respective distance plus m2 multiplied by r2 square plus m3 r3 square, right, plus so on. If there are n number of particles, if there are n number of particles in the body, then we can write mn rn square, or simply we can write I is equal to summation of mi ri square. Okay, I hope you got it. So it's a very important definition for rotational motion, and you know it is denoted by I, and unit will be kg meter square, kg into meter square. Okay. So now we are going to see the next term, that is radius of gyration. Okay, dear student, so definition of radius of gyration can be defined as if the total mass of a body is considered at a point, and if the moment of inertia of that point mass with respect to an axis is equal to that of the whole body with respect to the same axis, then the distance of the point mass from the axis is called radius of gyration with respect to the axis. As shown in the figure, now we can consider, suppose this is a rigid body whose total mass is m, and m1, m2, m3, m4 etc. denotes the masses of the individual particle. So dear student, according to the definition, if the total mass of the body is considered at a point, suppose total mass is considered is denoted by the point which is marked by red mark, that is total mark of the body is here m, and if the moment of inertia of the concentrated mass, if the moment of inertia of that concentrated mass with respect to the axis is equal to the moment of inertia of the whole body with respect to the same axis are equal, then the distance of the concentrated mass or point from the axis of rotation is called radius of gyration, which is denoted by k. So in that case, distance of this portion is called radius of gyration of the body with respect to the axis. So it is denoted by k. Denoted by capital K, and its unit will be, unit is, it's a distance, so unit will be meter, right? I hope you got it. So there is one, you need to memorize these two definitions, that is moment of inertia and radius of gyration. These are very important definition for the rotational motion. Now we are going to see an important expression of moment of inertia, that is a special case, moment of inertia and radius of gyration of a thin uniform rod about an axis through its center and perpendicular to the axis. So in the figure, dear student, suppose AB indicates a thin uniform rod and CD is an axis which is passes through the center of the rod and which is perpendicular to the rod. So we need to determine the moment of inertia of the rod about the axis and radius of gyration of the body. Dear student, first, to determine the moment of inertia of the body, we need to consider a small portion from the rod for simplicity or for better realization. Suppose the small portion or very small portion of the rod is denoted by dx, which is situated at a distance of x from the axis of rotation. Okay. So to determine the moment of inertia of this portion, of the selected portion with respect to the axis, we need to determine the distance of the portion from the axis, which is denoted by x, but we don't know the mass of the portion, because moment of inertia is m multiplied by r square or distance square. So here m is unknown, but mass is total mass of the rod is denoted by capital M, and total length of the mass is denoted by L. If we determine the mass of unit length, so mass of unit length is, we will get m divided by L. If total mass is denoted by total length, then we will get mass of unit length, but we need to determine the mass of the dx portion. So therefore mass of dx portion is, so m L into dx, right? This is the mass of this portion. So first we need to determine the moment of inertia of this portion with respect to the axis. So now we can write moment of inertia I, if denoted by di, since this is a small portion, so the moment of inertia can be denoted by di. Di is equal to mass, here m is m divided by L into dx, m divided by L into dx multiplied by square of the distance, which is x, so it will be multiplied by x square. So dear student, this is the expression for the moment of inertia of this selected portion with respect to the axis of CD. So we can simplify it, m L square x square dx. But we need to determine the moment of inertia of the total rod or total body, and for that we need to integrate this expression to get the total moment of inertia. So total moment of inertia, if denoted by I, so we can write integration of m L x square dx, and the limit will be, since the total length is L, so distance of every particle or the particle to the extreme point can be expressed as L by 2 and L by 2. So here the limit of the integration will be minus L by 2 to plus L by 2, right? So dear student, after the calculation you will get here m and L. at the constant quantity, so we can take it outside from the integration m by L integration of minus L by 2 by plus L by 2 into x square dx, right. So m by L, after the integration x square with respect to x, you will get x cube by 3 L by 2 minus L by 2. So using the limit in the expression, you will get here 3 is a constant quantity, so we can write m by 3L into x should be replaced by L by 2, so it will be L cube by 8 minus L cube by 8, and it will be plus, so L cube by 8. So it will be m divided by 3L multiplied by 2L cube by 8. So after the simplification, dear student, you will get I is equal to m L square divided by 12. This is the expression for moment of inertia of a thin uniform rod about an axis passes through the center and perpendicular to the axis. Okay. Now, if the radius of gyration of the rod with respect to the axis CD is denoted by k, that is radius of gyration is denoted by k, then according to the definition of radius of gyration, m k square is equal to m L square divided by 12. So after the simplification, that is omitting m from the both side, you will get k square is equal to L square by 12. Therefore, k is equal to L divided by root 12. So dear student, this is the expression for radius of gyration, and this is the expression for moment of inertia. Okay, I hope you got it. Dear student, now we will see some expression for the moment of inertia and radius of gyration for some special cases. That is, in case of thin uniform rod, when the axis passes through the center and perpendicular to the axis, that the moment of inertia will be m L square by 12, and a radius of gyration will be k is equal to L by root 12. That is, we have already proved in our classes. But if the axis of rotation passes through one end of the rod, so in that case moment of inertia I will be m L square by 3 and radius of gyration k will be L divided by root 3, right. So moment of inertia in case of a thin circular disc, when the axis of rotation passes through the center and perpendicular to the center, then moment of inertia will be I is equal to m r square divided by 2. Here r is the radius of the disc and radius of gyration will be k is equal to r divided by 2. But if we determine the moment of inertia of the disc with respect to its diameter, so in that case moment of inertia will be I is equal to m r square by 4 and radius of gyration will be r by 2. So dear student, these expressions are very important for your MCQ exam and for creative question, because we need to use the expression to solve some mathematical problem. Okay. Dear student, now we will see the expression for I and k, that is moment of inertia and radius of gyration, for some more special cases. That is, if we determine the radius of gyration and moment of inertia of a cylinder with respect to an axis passing through the center, like the figure, so in that case moment of inertia will be m r square by 2. Here r is the radius of the cylinder and radius of gyration will be r divided by root 2. Moment of inertia of a circular ring with respect to an axis passes through the center like this. So moment of inertia will be I is equal to m r square, and in that case radius of gyration will be k is equal to r, exactly equal to the radius of the circle or ring. But moment of inertia of a solid sphere like this, in that case moment of inertia will be I is equal to 2 by 5 into m r square. So, and radius of gyration will be k is equal to root over 2 by 5 into r, and that for the hollow sphere, that is moment of inertia for the hollow sphere, it will be I is equal to 2 by 3 into r square. For the solid sphere it will be 2 by 5, and for the hollow sphere it will be 2 by 3 r square. Okay, and radius of gyration will be root 2 by 3 into r, right. So, dear student, I hope you got it. Already I have mentioned that you need to memorize this type of expression for your MCQ exam and creative portion. Okay. So, dear student, now we are going to see some mathematical problem and creative question regarding to the expression or based on the topic discussed in our today's class. Right. Here is a mathematical problem, and the mathematical problem, they said that an electric fan revolves 1500 times per minute and stops in 4 minutes after switching off. What is the angular acceleration and how many times will it revolve before stoppage? Right. So, dear student, here the given information that the fan revolves 1500 times in 1 minute. So, from the information we can determine the initial angular velocity of the fan, right. Here initial angular velocity which is denoted by omega naught. Omega naught is equal to 1500 multiplied by twice by divided by 60 in 1 minute, right. So, after the calculation it will be 50 pi radian per second, right. This is the value of the initial velocity. Okay. Now, the given time t is equal to 4 minute, that is 4 multiplied by 60. So, it will be 420 second. Final angular velocity omega is equal to 0. So, we need to determine the angular acceleration alpha is equal to what, and number of rotation. So, there is shown, we know angular acceleration alpha is equal to omega minus omega naught divided by t. Okay. So, using the value of omega naught is equal to 0, omega is equal to 50 pi divided by 240, and after the calculation you will get 0.654 minus 0.654 radian per second square. This is the angular acceleration of the fan. Now, we need to determine the number of rotation or revolution before stoppage. So, for that first we need to determine the total angle subtended or created by the fan before its stoppage. So, here total angle we can determine total angle theta is equal to omega naught plus omega divided by 2 multiplied by t, right. So, 0 plus it will be 50 pi divided by 2 into 240. So, after the calculation you will get 6000 pi radian. This is the total angle that the fan makes before it come to rest. So, number of revolution, for twice pi angle the number of revolution will be 1, or in one revolution it will create twice pi. So, number of revolution can be obtained by dividing this total angle by twice pi. Therefore, number of revolution (6,000 pi divided by twice pi). So it will be 3,000. Okay. So number of revolution will be 3,000. So dear student, the angular acceleration that we have calculated earlier, that was minus 0.654 radian per second square, and number of revolution will be 3000. Okay, I hope you got it. Dear student, here is a creative question. In the question they said that a uniform disc like figure 2 is made by a uniform rod in figure 1. That is, this disc is made by the rod. Here the parameter or length and mass for the rod is, length is 60 centimeter and mass is 0.5 kg. We convert the rod into disc like the figure. Here the question C, past question said that determine the moment of inertia for figure 1. So we have to determine the moment of inertia for the figure 1. Dear student, you know, here the moment of inertia of a thin uniform rod in which the axis of rotation is passes through one end of the rod. So we need to determine the moment of inertia of the rod. For the solution of C, here length L is equal to 60 centimeter, it will be 0.6 meter. Mass M is equal to 0.5 kg, right? So moment of inertia, we know moment of inertia in case of the rod when the axis passes through one end, it will be m L square divided by 3. So using the value m 0.5, L square 0.6 square divided by 3, and after the calculation you will get 0.06 kg meter square. Therefore I is equal to 0.06 kg meter square. Okay, this is the moment of inertia for figure 1. Now in question D, they said that if the circumference of the disc is equal to the length of the rod, then in which case moment of inertia will be more. Explain. So dear students, since to determine the moment of inertia of a disc, we need radius of the disc. Here radius of the disc is unknown, but we will be able to calculate the radius using the information that the circumference of the rod will be equal to the length of the rod. So from the information we can determine the radius, but the mass of the disc will be same as usual the mass of the rod, because from the rod the disc is made. Okay. If radius of disc be r, then 2 pi r, that is circumference, it will be equal to the length of the rod, that is 0.6, or r is equal to 0.6 divided by twice, and it will be 0.0955 meter. And you know mass will be the same, that is m is equal to 0.5 kg. Therefore moment of inertia in figure 2, that is the moment of inertia of the disc with respect to the axis passing through the center, if denoted by I prime, then it will be am r square divided by 2. Here m is 0.5, r square means 0.0955 square divided by 2, and 0.0028 kg meter square. But in case of the rod, it was I is equal to 0.06 kg meter square. So dear student, after the calculated value we can say that I is not I prime. Okay? Or they said that in which case moment of inertia will be more. So we can write that, so in case of rod the moment of inertia will be more. Okay? So dear student, I hope you got it, and I believe that this class will help you a lot for your upcoming exam, and good wishes for all of you. Thank you very much being with me in my class. May Allah bless all of you. Assalamu alaikum.